So, in most math courses, we tend to focus our attention on the study of functions and their properties because they provide a means to abstract many algebraic manipulations. This level of abstraction helps us to more easily apply techniques to a broad range of problems. So, our goal is to use these familiar ideas to develop a language of functions for linear algebra. So, in order to do this, we're going to review some properties of functions, specifically functions defined on sets. So we're going to start off with the basic building blocks of functions, and we're going to establish a dictionary between this familiar language and the terminology that we have developed in this course. So the first one is we're going to start out with the domain and codomain. So recall, the set of all possible inputs to a function is called the domain. The set that contains all possible output values of the function is called the codomain. For example, if we are interested in studying the square root function in a basic algebra course, then we would normally write f with a colon, square bracket 0, comma, infinity, parenthesis, and then an arrow to the math bold letter R to indicate that f is a function that accepts non-negative real numbers as input and outputs real numbers. So this arrow notation is a nice shorthand that indicates where we start. So we choose a number that is at least as large as 0. We take its square root, and then we end up with a real number. So if we decided to be a little bit fancier in our study of the square root function, then we know that it's actually possible to extend our domain to the set of all real numbers. In this case, we would write f colon r to c to indicate that f is a function that accepts real numbers as input and outputs complex numbers. So it's important to remember that the domain of the function is actually a very important piece of the actual function itself. If we change the numbers that we allow inside of the function, we actually do get a dramatically different function. Namely, the first one always outputs real numbers, while the second one, if we allow, say, -1, for example, its square root is the complex number I. So far in this course, we've been interested not in looking at single numbers at a time, but collections of numbers in the form of vectors. So it's not unreasonable to expect that our functions should take vectors as input, and it should also output vectors. So we're going to define the matrix A, which is a 3x4 matrix. So we remember that we've defined matrix vector multiplication simply by saying if I choose any 4-dimensional vector v, then I can multiply v by a on the left, and I'll get a linear combination of 3-dimensional vectors, which is, of course, itself simply a 3-dimensional vector. So we could think about this type of association as a function. This is a function, which we're going to call t. It takes in as input a 4-dimensional vector, v, and it outputs a 3-dimensional vector, av. So we've expressed this with two lines. So the first line of our function definition tells us the name of the function is t. It says t accepts a 4-dimensional vector and it outputs a 3-dimensional vector. That's the R4, the arrow, and then the R3. On the second line, we've given a name to the input values. So since we're thinking about vectors instead of numbers, we use the variable v for vector. So this second line says v is a 4-dimensional vector, and this funny arrow with a bar on the left-hand side is the maps to symbol. So this second line says v, this four-dimensional vector, maps to the three-dimensional vector av. This is also, of course, equivalent to expressing our function as t of v is equal to a times v. Now, there's nothing particularly special about this matrix A here. In fact, if we take a general matrix, which is composed of n m-dimensional vectors, v1 through vn, then such a matrix will always define what we call a matrix transformation, T, which accepts n-dimensional vectors as input and outputs m-dimensional vectors, defined by T of v is equal to a times v. So these are going to be essentially the fundamental functional building blocks for this course. So anytime we're talking about a function in the context of linear algebra, we're almost always going to be talking about matrix transformations. If you've taken a course like multivariable calculus in the past, you've likely encountered functions of more than one variable. So this is the multivariable part of multivariable calculus. These are a specific type of multivariable functions. In fact, they are the linear multivariable functions, which we'll see later.